Hello, welcome to Statistics for ESS. Actually, this is just an introduction to a couple of tests that you can use when you are doing an investigation where you're using a lot of data, especially data. This data could be data that you take yourself in a lab, or it could be data that you have mined from a secondary source, which is the data that we're using today. So today, what we're going to do is I have collected data from the footprint network and about the ecological footprint of a bunch of different countries. And I've also gathered the data of the Human Development Index of a number of different countries. And we're going to look at a couple of different ways that we can analyze this data to determine if there's any statistical relationships between things, differences between means, and so on. So before we start digging into this, you're going to want to go to the folder in our ESS folder here. It's the ESS folder. There's a subfolder called IA Stuff, and then under there is the folder of statistics. And so in there, you're going to find both the Google Slides presentation I'm going over right now, as well as an Excel document for HDI versus EF, an example. You want to download that example. Now, hopefully, because the example I'm going to be using the latest version of Excel, which it is, I downloaded this in 2020. You can get it from the tech department, the IT department here, if you haven't downloaded it already. So make sure you download that because we've got to be able to use it actually on your computer. Okay, so let's take a look at some of the statistics that we're going to be looking at today. So a couple of things that we might want to consider are questions that we could ask that have to do with two numerical values and how they're related to each other. In our example that we're going to use, I'm going to show you on this Excel sheet. I have both the Human Development Index for a country and the ecological footprint for a country. So this is continuous numbers for both my independent and dependent variable. With that, I can make some comparisons. I can see if those variables are related to each other and in what manner. So different tests, the one we're really going to look at today is the R squared. That's the coefficient of determination. We've used it in this class before when we did our productivity lab. But there's also the Pearson's R correlation, which you use this Pearson's R correlational test in probably your math class. So it's looking if there's a direct relationship between your two variables. So as Human Development Index goes up, what happens to the ecological footprint? And then the next one that we'd be looking at is Spearman's rank. And the Spearman's rank is similar to Pearson's R, except for we're looking at the data in data that happens to be ranked. So it isn't necessarily, an absolute value, but it's like first, second, third, fourth, fifth, and so on. But today, as I said, we're going to focus on the example of the coefficient of determination, this R squared value. Now, another thing that we can do with this data is we can compare means. And so if we're comparing the means of two things, like the means of the ecological footprints in Asia versus the means of the ecological footprints in Europe, then if we want to compare, two means from two separate groups, we would use a t-test. Let's say we wanted to add another category in there. So we've got Asia footprint versus European footprints versus North American footprints. So we've added a third category. And if that's the case, we can compare means using an ANOVA. Today, the example I'm going to go over is using multiple groups. So we will look at an ANOVA. So we're going to look at two tests today. We're going to look at the R squared coefficient of determination for the data that we've got and an ANOVA. So the first thing we're going to do is we're going to compare two variables using this question. What is the relationship between the Human Development Index of a country and its per capita ecological footprint? In this case, our independent variable is our HDI, and our dependent variable is the per capita ecological footprint. So first, let's define our development index so you're familiar with it. That's a statistic that basically ranks countries on a scale from 0 to 1, and they base they give that country a score based on the life expectancy, education, their income, general well-being type things, healthcare, and so on. And the higher you are, so the closer your value is to 1 for a country, the greater your development index, the longer the lifespan, better education levels, better, more income, money, so on and so forth. So closer to 1 is generally better quality of life, whereas closer to 0 is usually not as good of quality of life. And so what we're investigating here in a couple of different ways is we're going to say, okay, how does this score that a country has on its Human Development Index, as that score increases, what is the responding ecological footprint? So how does one's HDI ranking generally show, is there some sort of pattern between that and the ecological footprint that a country has? And we know that ecological footprint is the land and water required per person to sustainably support a defined human population at a given standard of living. And so that's going to look at how many hectares of land is necessary per person, because it's per capita in this example. How many hectares of land does it take to provide all the resources they need? And how many hectares of land do they need to be able to assimilate all the waste? So that combined is going to be the footprint per person. So the waste might be carbon dioxide or pollution or whatever. Okay, so take a look here. I have the HDI score of all of these countries. So this is the lowest scoring country here, with Niger all the way up as we're increasing. I sorted it from lowest to highest to the highest scoring, which is Norway, of the HDI index. Okay, and next to it, so here's our independent variable. And next to that, we have our dependent variable, which is the ecological footprint for each of these countries. So I have both the score, independent variable of the HDI, and the number of hectares needed per person to meet all their needs. So we're going to see, okay, as these numbers go up, what tends to be happening to the ecological footprint of a country. These two rows we don't really need. That's just for general interest that I left them there. We really need to make sure whenever we're putting things together that we have our independent variable on the left and our dependent variable on the right. So when we're graphing, we can get everything on the right axis. Okay. So in doing all this, I've already pulled the data for you, and you put your independent variable in the first column, your dependent variable in the second column, and we're going to now graph this data, okay? So to graph it, I'm going to highlight the two important columns, and I'm going to go to Insert, Chart, and we want an XY scatter. That's because we have an X and Y variable, essentially. The development index is our X, and our Y is our footprint. So here's our scatter. I don't know why it picks up this extra label, which I'm just going to erase. And I can make it quite a bit bigger for you here, so we can kind of look. All right, so it looks like there's some sort of pattern happening. Each one of these points is an X and Y variable. If we were to look at this, one point at a time, you could correlate them to where they are on the graph. We can see this lowest human development index of 0.377 has a footprint of 1.5, so right there. Okay, and the highest one, which was Norway, I think. Well, the highest development index was Norway, which is somewhere in here, is 0.9 for the index, and then 5.8 for the footprint. So you can kind of look through those. Okay, so first, what we need to do is actually, on our graph, we need to label our axes so we know what we're doing here. So our horizontal axis, I'm going to just give a title. It's the HDI, right? And then our vertical axis, I will give that a title of our per capita ecological footprint. Okay, so we're at least labeled now. Okay, so now we're going to basically determine the R-square value, and we can do that very easily just using Excel by adding a trend line. So generally, when you go into trendline, you don't want to pick any of these normal ones. You want to go straight to more trendline options. Okay, so I'm going to click on that, and I have this box that came up on the side. So right now it's chosen linear trendline. And the other thing you're going to want to do is display the equation on the chart and display the R-square value on the chart. Okay, so I'm going to move that so you can actually see what those numbers are. So you can see we have a trend line, the y equals mx plus b. So that's that line. That equation describes that line. And here's our R-squared value. So the R-squared value is essentially telling us how well our data fits that trend line. How well does it land on that line? And it's also letting us know how reliably we can use this equation to make predictions. So if we had a development index of, say, 0.5, if we were to plug that X into the equation, how well would that predict the actual Y value, the ecological footprint value, based on the equation? Now, this is different from the correlation coefficient that you learned, the Pearson's one, that is just the R, because that one is only pretty much looking at how well these data points are correlated to each other. So is there a correlation between my independent and dependent variable? So this one goes from 0 to 1, my R-squared value. And the closer it is to 1 means the stronger the fit of the data is to that line of best fit that you selected. So 0.55, it's not super strong. It's showing that there's a relationship there. But I think there's probably something else going on with this data. It seems to be more of an exponential movement here. So I'm going to select exponential. And you can see with that exponential, we have, of course, changed the equation because we have a different line, and which is very light. Let me see if I can find my line here. Okay, it's hard to see the line, so I'm going to actually format that trend line. So I'm going to go over to my trend line options, open up that side chart here. Here's my exponential. I can't see it very well, but I think that I can format that with this dash type. It's kind of little and light, so I'm going to give it a solid line so you can kind of see it in there. I'm going to make it a little bit darker. I might even change the color, if it lets me. There, we could even change the color to like a darker blue if we wanted to. So here's our exponential line at this point. And you notice what happened with the R-square value. It is now 0.7, which is showing a stronger correlation than the line did, which makes sense because it really looks like the data is moving. So what does this tell us? Well, if there's a strong correlation between this line of best fit, it's essentially saying that there is an exponential relationship between development index and per capita footprint. You notice that as your development index gets bigger, your ecological footprint is getting bigger, but at an exponential rate. It's not just linear. One goes up, the other kind of goes up. So this is an interesting way to really look at this data, to be able to actually see kind of, oh, okay, so this is not just a normal linear relationship. There's other ways that, depending on what your data is, if you were looking at like the optimal pH to grow plants in a soil, you could use the polynomial to be able to, get this nice curve and select the optimal. But for this data, this seems to be the best fit. Okay, so we've displayed it, and we've displayed our data, and our R-squared essentially told us how well our data fits the trend line, and we picked that exponential, and it seemed to fit it pretty well. So the closer it is to 1, the more perfectly it fits the trend line. There's 2 other tests that we can do on this type of data, but we're going to just gloss over those for now and head straight to comparing means. So we're going to ask a slightly different question with the same data. Um, the question we're going to look at is pretty much the same question, right? What's the relationship between Human Development Index and the per capita ecological footprint? But it turns out that the development index can also put countries into categories based on what their index is. They put them into 4 different groups. So you notice that I've color coded this into 4 different colors. So the lowest I have as like a pinkish color, and then the next one is kind of a yellow, and then a blue, and then a green. So this is the highest index. So they've kind of grouped these countries into 4 different categories. And since we've got categories, if we were to look at the mean footprint for each of the development categories, low, medium, high, and very high, we can use a different type of statistical test because we're grouping them differently. So what I did is I grouped the data differently. We no longer need this numerical value because we just need to know if they're low, medium, high, or very high. So this next tab down here, you can click on that and see that I have now put the data. I have the country here. We don't really need the name of the countries for this, but I did for sheer interest in keeping track of it. But here's the footprint for the low index. Here's the footprints for that in the countries that have a medium, high, and then very high. And you'll notice there's a different number of countries in each. So what we're asking in this question is, does the mean footprint, how does the mean footprint for these 4 different categories of development index compare? Is this one higher than this one? Is this one higher than this one if we take them all and take a mean? So we're going to do an ANOVA to ask this question. So if we just had 2 groups, we'd do a t-test, as I had mentioned before, but we're actually going to do an ANOVA because we have 4 groups in this case. So the null hypothesis for an ANOVA is that the mean of group 1 is equal to the mean of group 2 is equal to mean of group 3 is equal to mean of group 4. So what we're essentially saying is that the mean ecological footprint of the low index is equal to the mean ecological footprint of the medium is equal to the mean ecological footprint of the high is equal to the mean ecological footprint of the very high. And when we plug the numbers into an ANOVA, we end up getting, it spits out a p-value. And the p-value is going to tell us whether we accept or reject this hypothesis. If our p-value is less than or equal to 0.05, we will reject the null. And that will say, okay, actually, all these means are not necessarily all equal to each other. We don't know which ones. We don't know if it's 1 is not equal to 2 or 1 is not equal to 4 or 3 is not equal to 4. But we do know that this statement is not true, statistically speaking. So we're going to kind of go through how to do the ANOVA, and thankfully there's a calculator. You don't have to, run it yourself. But before we run it, we're going to set up the data and graph it. So when you're setting up the data, when you're comparing means, you want to record the following for each group. You need the mean, the sample size, the standard deviation, and the confidence intervals, okay? And the sample size is just how many are in each group. So the sample size for these would be how many countries are in this group. So it looks like there's 36. So if you were to go through and count how many different countries are here, there's about 36. And here there's probably about 31, so on and so forth. So we would count how many are in each of these. The standard deviation is the spread of that data around the mean. So if you have a mean ecological footprint, let's say of 5, how is your data really close to 5? Or are all the countries in that group really close to around 5, or are they spread out quite a bit? So a larger standard deviation gives us less reliability in what the mean actually is, whereas a closer one saying that it's grouped together pretty closely around the mean. The 95% confidence intervals are going to be important to be able to tell us which groups are and aren't statistically different from each other when we do this ANOVA. And what that is telling us is that if you were to take these measurements 100 more times, well, 95 of those times, the mean that you are calculating would probably fall within that range, okay? So we're gonna graph our independent dependent variable after we get all of these things first. Okay, so we need to set up a table that has all of this data for us. So what we have is our HDI, and we have low, we have medium, high, and very high, okay? And then we have our mean EF, we have our sample size, we have our standard deviation, and we have our 95% confidence intervals, okay? The mean is, we'll simply use an equation that we can go over to the FX button and click it here, and it will give us our formula builder. And I'm going to double click on average, okay? Now that's not the average I want. I don't want to take an average of 4.3 and low. So I'm going to tell it what I want it to take the average of. So this is the average. I want the average footprint of low. So I'm going to click in this first box here, and you see that's B3 and that's B3, okay? Then I'm going to just put in a colon, and then I'm going to go down to the very last number that I want in that column, and you can see it highlighted everything there, which is exactly what I want. So from B3 to B38, okay? And I hit done. I'm happy with that. For my medium, I'm going to do the same thing. I'll double click on average. I'm going to tell it this is my first value and this is my last value, okay? And I hit done. Make sure you get that cursor in the right spot, average. You can also highlight, you know, the numbers that you want. That works as well. It's a little bit clunkier sometimes, but that works just the same as if you were putting in that colon yourself. Okay, and then my very high, I do that last one again. And oops, I forgot to double click my average. So I'm going to tell it that I want it to be from here. Oh, I'm in the wrong box. It's very disappointing when I do that. I want my box to be here. So I'm going to hit done because I'm very unhappy with what I just did. See, if you don't have it in the right box, it's very upsetting. Let's see if I can get my data back by just hitting the backspace. I did. Good. All right, so here's where I want my average to be. I'm going to double click, and then I'm going to select all this data, and I hit done. Here's my means for each of mine. So you see my mean ecological footprint is 1.2, 1.6, 2.9, and 5.5, obviously getting bigger, which makes sense because that's what we looked at last time. All right, and then sample size is just, you can get that by doing the count. You can eyeball it if you want here to get the right number, but nice and easy, I can just do the count. I'll double click and I just do the exact same thing that I did before. Hit done. My count for the medium. Oops. Always got to make sure you've got your clicker where it needs to be. Okay. All right, so now I have my sample sizes. You notice they're not the same. Your sample sizes do not need to be the same. That does not matter in this case. And we have very nice sample sizes. Having sample sizes of 30 or more is generally kind of what you're aiming for. All right, standard deviations, the next thing. So we're just going to go through and do it the same way I did before. Just going to highlight the numbers I want to include in my standard deviation. So, and always make sure you're in your box and doing what you need to do. And my ecological footprint. And my last one for very high. And done. Okay, so there's my standard deviation for all of them. And then my confidence intervals, actually a little bit easier to do because I don't have to highlight all that data. So I want to put my confidence interval for the low data here, and I'm going to select confidence norm. You might need to do a search for it. So I'll double click that. And it needs 3 numbers for me. The first number will be the same for all the times you're doing this. We're doing a 95% confidence interval. So we want any outliers, any mistakes to only happen by, 5% of the time. So I'm going to put in 0.05. Okay. My standard deviation, already calculated that. And my size, that's my sample size, is 36. And I already calculated that. So you can just click in there. So you see those all correlate. So I hit done. And then you can drag the tab down because it all seems to correlate quite nicely. So we have all the data we need. Okay, so we have our mean, our sample size, our standard deviation, our 95% confidence intervals. So the next thing we're going to do is we are going to graph our data. So again, independent variable goes on the x-axis and the dependent variable goes on the y-axis. And we're going to make a column graph and use the 95% confidence interval for our error bars. So here, I'm going to highlight the data I want to graph. It's only the mean, footprint, and the category. So my independent variable and my dependent variable. Insert chart. This time it's going to be a column chart. And it nicely pops up here. We can make it nice and big. I'm not going to put the title in there. The title can go when you drop it into the report. And of course, our axes titles. HDI category. And then for our horizontal, oops, that's my horizontal again. I want my vertical. Okay, here's my vertical. Put that in there. And this is my per capita ecological footprint. Okay, and that's in hectares, so I should probably put the units there too. All right, so we've got low, medium, high, and very high, and that seems to make sense with what we have for our data here. Now, the next step is to add the error bars for the confidence intervals. So I'm going to add chart element, and I'm going to go to error bars, but my error bars, I'm going to more error bar options. Okay, and can you see behind here? I don't need my formula builder, so I'm going to close that. I'm with my error bars here. And my error bars, click on the one that has the bars to get you to the format error bars part that you want. And I'm going to do a custom error bars because it's got something in here that does not correlate with those values. So it's meaningless to me. I want to put in the confidence intervals for each. So I'm going to hit custom and specify value. So I can move this over to the side. What I'm going to put in here and here are the same thing. I just want to highlight so I can erase where that is, and I highlight the confidence intervals, those 4 values. So you can see it's just those 4 values that have been highlighted. I hit OK, and you can see that now those confidence intervals are individual for each of the categories. This one has the largest confidence interval, so it's got the largest error bar. So if we were to take this measurement 100 more times, 95 of those times it would fall, the mean would fall somewhere between here and here. Okay. And obviously the smaller the confidence intervals, the closer you are to the mean with that. Okay, so there's our graph. Last thing we're going to do is we're going to run our ANOVA. Okay, and thankfully you don't have to calculate it yourself. There's a calculator for that. And you're going to basically cut and paste the raw data for each of the EF values into the calculator, and it's going to give us our p-value. So here's the calculator. You can follow that link. And the calculator gives us the option for 5 treatments. We only have 4, so we'll just plug in 4 sets. So for treatment 1, I'm going to put in the low. So I'm going to highlight, and basically I'm going to copy all of that data. And for the first value, and I'll put it in there. And then for my next treatment, I'm going to do the medium. And for my next treatment, I'm going to do the high. Copy it and paste it. And then for my last treatment is the very high. So I'm going to copy it and I will paste it in here. And then you scroll down, 0.05 significance is good. That's saying that we want to be 95% sure that we're appropriately rejecting the null if we need to. And we calculate. It says we successfully did it. Yay. Okay, so there's all of our data, and here's the summary of our data. It gives you the sample size of each of them. It gives us the mean of all of them, and so hopefully those match what we did here, so our sample sizes and our means. Okay. It gives us our standard deviations, which hopefully are similar for each of those groups. And then the key value that we're looking for here is the p-value. So see this p-value here? It's less than 0.00001. So I'm going to just copy that and I'm going to stick it down here so I have it. That's our p-value for our ANOVA, right? And if you remember, when we were back on our slides, if our p-value is less than or equal to 0.05, we can reject the null. And the null was basically saying all values are equal. But that's not the case because we're rejecting our nulls, so they're not all equal. It doesn't, however, tell us which values might or might not be equal. It's only telling us that at least two of the values aren't equal. There is definitely a statistically significant difference between at least two of the means. It could be two or more. The way we can actually figure out which means that are different from each other is by using the confidence intervals, those 95% confidence interval error bars. If the error bars overlap, there's not going to be a significant difference between those two groups. If there's no overlap, then there should be a significant difference between those two groups. So take a look here, and we can see between very high and high, there's no overlap. In fact, for very high, it doesn't overlap any of these. So definitely the means between very high and any of the other groups do not overlap. They're not the same. They're statistically significantly not the same. High, same thing. There's no overlap, no overlap. So this mean is statistically different than the others. However, if you look at low and medium, there's overlap here. So although they have the medium has a higher mean than low, it's not a statistically significant difference. So we can't say that these two have a different footprint than these two. And look, this looks just like an exponential curve that we had going on before, doesn't it? So we're just two different ways to look at the data. So in this case, very high shows us that it's got a very high development, has a very high footprint, and the mean of that is different, statistically significantly different than the other groups, and so on and so forth. But these two are not different from each other. So low and medium has pretty similar footprints, but once you get into the high and very high, the footprint seems to be quite different. Okay, so that's looking at essentially the same question in two different ways, just based on if you have categories of data, like maybe you would compare categories of, if you could look at Asia, as I said, versus Africa versus North America, so you could compare those means. Or if you have continuous data like HDI versus EF. I mean, it doesn't have to be HDI versus EF. It could be ecological footprint versus education levels. So as long as you have two continuous numbers, you can do something more like this. And when you have groups, you would do something more like this. Okay, hopefully this was helpful.